In this video, I want to talk to you all about the concept of redox reactions, what they are, what it means, and how to spot them. I want to start off with a couple of reactions that you actually would be able to pigeonhole into a certain reaction type based on a previous video and what we've seen before. When you have, for example, solid iron and oxygen gas making iron oxide, this is rust, two species coming together to make one is known as a combination reaction. You've seen that before. Solid magnesium and HCl making magnesium chloride and hydrogen. Here, the magnesium steals the chlorine from the hydrogen. This, what you've seen before, is a single replacement reaction. So technically, two separate reactions. However, these and actually a whole bunch of others can all be classified together under one particular umbrella, and that is the umbrella of redox reactions. Redox, of course, is short for reduction and oxidation. Reactions where electrons are transferred from one species to another. Something gets oxidized, something gets reduced. It's all about the electrons, all right? And the simple way to remember what's happening here is to remember the simple mnemonic oil rig, all right? When something undergoes oxidation, it loses electrons. So something being oxidized is losing electrons. Something undergoing reduction or being reduced is, of course, the opposite. And that's gain, because if something loses electrons, something else has to gain them. All right. So what we'll do is we'll look at each of these two reactions in detail and see how we can tell that they are redox reactions, and then we'll look at some others and see if we can figure out if we can tell, just given a reaction, if it's redox or not. So let's look in more detail at this one. So the simple way to tell if something's a redox reaction, there's actually a couple of different ways. If you have any elements that are by themselves anywhere in the reaction, it's a pretty good sign that's going to be a redox reaction. And when I say by themselves, I mean not with any other elements. Like iron is here on its own, oxygen is here on its own, and over on the other side, they're not on their own. So if things are on their own on one side and not on the other, that is a very good sign it's going to be a redox reaction. So how do we tell for sure? Well, what we need to be doing is looking at the oxidation states. Oxidation states on each of these. And what I mean by oxidation states is really charges. What are the charges on each of these? We've seen before how to do this. The only thing that's new here is what happens to something when it's on its own. All right. Any element, whether it's oxygen, whether it's diatomic or monatomic like this, whether it's iron or oxygen or fluorine or chlorine or whatever, if it's by itself with no other elements, it always is given an oxidation state of 0. And if that oxidation state or that charge changes on the other side of the reaction, that means it's a redox reaction. All right. So when we look at this, we have to figure out the charges on each of these two. Well, we've seen what charge oxygen forms before, because oxygen pretty much always forms a charge of -2. We've seen this before, O2 minus. And if each of the oxygens here is -2 for a total negative charge of -6, then each of the ions must be +3. So if we split this reaction up into the two separate species, we have iron that was originally iron 0, and it's going to iron 3+. So something is happening there, and this change in this charge here is due to electrons moving around. We've got oxygen, on the other hand, with a charge of 0 initially, going to oxygen with a charge of 2-. All right? So what's happening here is there is something happening in each case. One of these is an oxidation, one of them is a reduction. All right? If we go back to here, we said oxidation is loss of electrons, reduction is gain of electrons. All right? Electrons are negatively charged, so when you look at oxygen to oxygen 2-, it looks like this guy has gained something negative. And not only something negative, it's gained 2 negative. So it's gained apparently 2 of something that has a charge of 1-. What it's done is it's gained 2 electrons. All right? So we've gone from O0 to O2-. And here, this iron that was originally at iron 0 and has now gone to 3+, if you go from 0 to minus, you've gained electrons. If you go from here to here, it must mean that you've lost electrons. In this case, it's 3 electrons. Now, the actual number of electrons to determine what's going on is not important. What is important is the ability to recognize what's oxidized and what's reduced. Anytime you're drawing out reactions like this, there's always going to be electrons on the right-hand side for one equation and then on the left for the other. So what this means is, when we look at this first reaction, this ion 0 has undergone some reaction and lost 3 electrons to form this. So it's lost electrons. In other words, this has been oxidized. On the other hand, this O2 minus has gone to, this O0 has gone to 2 minus. It's gained electrons. It's been reduced. So anytime you're writing things like this out, anytime you have electrons on the right-hand side, that means whatever you're talking about here has been oxidized. Whenever you have electrons shown on the left-hand side, it means whatever you're talking about here has been reduced. And then the only other thing is, when you're determining what's oxidized, what's reduced, you're only looking at the species on the reactant side. These products here are just to show you what's happening, right? So in other words, the ion 0 was oxidized, and the oxygen was reduced. The ion lost electrons, the oxygen gained them. All right, let's have a look at this reaction. You remember when I said how to recognize a redox reaction? If you have something that's on its own on one side of the equation but not on the other, it's a good chance it's a redox reaction. Well, here we've got magnesium on its own on the reactant side and hydrogen on its own on the product side. Hydrogen is not on its own on the reactant side, and magnesium is not on its own on the product side. Therefore, good chance that that is a redox reaction. But let's figure out exactly what's oxidized and what's reduced. Well, when we look at the magnesium, initially it's got a charge of 0 because it's by itself. And when we go here, chlorine has a charge of -1. We know that. We've seen that many times before. And there's 2 chlorines, which means that's 2 minus, therefore magnesium is 2 plus. But we knew that because magnesium is in group 2. So magnesium's gone from Mg0 to Mg2 plus. And when we look at the hydrogen, here the hydrogen is on its own, therefore it's 0. All right? And I'm just showing each hydrogen atom here rather than the hydrogen molecule, so that's why there's no 2 here. And then on this side, what's the charge on the hydrogen here? Well, we said before, chlorine's -1, so hydrogen must be +1. So we've gone from H plus, or +1 or whatever, to H0. So when we look at the magnesium, this has lost some electrons. In fact, it's lost 2 electrons. Whenever we show something losing electrons, we show those on the right-hand side. That means this guy has lost 2 electrons. The hydrogen, though, has gone from +1 to 0, meaning it's gained something negative, which means the electron is on the reactant side. This has been reduced. So therefore, the magnesium has been oxidized. The hydrogen has been reduced. All right? When you balance all this out, these numbers will balance out as well as to why there's 2 electrons here and 1 here. But the important thing at this point is recognizing that you can write out these equations showing there's electrons on one side for one reaction and on the other side for the other. If you drew out 2 reactions like this where the electrons were both on the same side, that should tell you, oops, I've ballsed up somewhere. I'm sorry, I have messed up somewhere. Anyway, let me give you another couple of examples. Are these redox reactions? And then if they are, we'll figure out what is going on. Are these redox reactions? This is the first one to ask ourselves. This is another reaction. We haven't seen this one yet, but we should be able to classify. We've got zinc and copper sulfate going to zinc sulfate and copper. The zinc steals the sulfate from the copper. This is also a single replacement, just like the magnesium HCl one we saw. And we just want to ask ourselves, do we have anything that's on its own on one side that's not on its own on the other? Zinc is on its own on one side, it's not on its own on the other side. Copper is on its own on one side, it's not on its own on the other. Good sign, it's a redox reaction, so check that box for redox, alright? So let's look at the zinc to see what's actually happening. What's the charge on the zinc to begin with? On the left-hand side, well, it's by itself, so it's 0. And when we go over to the product, SO4, you need to know that SO4 sulfate is 2 minus, which means the zinc is 2 plus. On the other hand, for our copper, it's 0 over on the product side because it's by itself. It's not by itself here, it's with the sulfate, the same sulfate that the zinc was with. And if sulfate was 2 minus here, it's going to be 2 minus here, meaning the copper is going to be 2 plus here. So notice the opposite thing is happening. I'm going from 0 to 2 plus and 2 plus to 0. And that's good. That's the way it should look. Because the thing that's going from 0 to 2 plus is losing 2 electrons. The thing that's going from 2 plus to 0 is doing the opposite. It's gaining 2 electrons. And if you think back to what that actually means, this guy is spitting these electrons out. It's losing electrons. It's being oxidized. This guy is gaining those electrons to form this. It's being reduced. Therefore, the zinc is being oxidized. The copper 2 plus is being reduced. So not only was it a redox reaction, but we figured out what was oxidized and what was reduced. Let's look at this one too. Is this a redox reaction? Well, we've got sodium and sodium chloride, silver nitrate, silver chloride, sodium nitrate. Notice in each of these we've got 2 partners, two elements per molecule here, at least. Sodium's originally with the chlorine. Over here, silver's with the chlorine, silver's with the nitrate, sodium's with the nitrate. Is there anything in this reaction that is on its own on one side but not on its own on the other? And of course, the answer to that is no. This is a double replacement reaction, and these are very, very rarely redox reactions, and let me show you why. The charge on sodium here is what it always is. It's +1. Nitrate is -1, so the charge on sodium here is +1 as well. So from the reactant to the product, the charge hasn't changed. That's a bad sign for if you want in a redox reaction. Nitrate is 1 minus. We saw that over here, so that means the silver is +1 here. The chloride is -1, so silver is +1. Notice neither of my metals have changed their charge from reactant to product. That means no chance for a redox reaction. There's no need to look at all the others. You'll get the same answer. If the charges of the metals or species are the same on each side, no redox. All right, one more. First question. Is there anything that's on its own on one side but not on its own on the other? And of course the answer here is yes. In fact, there's 2 of them. Silver is on its own on the product, not on its own in the reactant. Bromine is on its own in the product, not on its own in the reactant. So clearly something is going on as far as redox goes. So click, check for redox. Bromine. What's the charge on bromine? Well, you know bromine forms charge of -1. It's in group 7. And it's going to bromine on its own, which is Br0. Silver, on the product side, is on its own. It's going to a charge of 0. However, it's not on its own to begin with. If bromide was -1, silver must be +1. So we're going from negative to 0. So this guy must be losing an electron to go from -1 to 0. And that is exactly what is happening. The silver plus is going from +1 to 0, meaning it's gaining an electron. In other words, something's been oxidized and something's been reduced. Well, the Br minus is spitting out an electron. It's being oxidized. It's losing that electron. The silver plus is gaining that electron. It's picking it up. It's being reduced. Meaning the Br minus is oxidized. The silver plus is reduced. That is how you spot redox reactions, and once you spotted them, that's also how you can tell what's being oxidized and